Okay, so you know how in math sometimes you run into these concepts and you're like, when am I ever going to use this in real life?
Right.
Like, when's the last time you needed to find the square root of -1?
Yeah, it's not exactly something you need to balance your checkbook or anything.
Exactly, but that's what I love about this deep dive we're doing today. We're tackling imaginary numbers, which sound like something straight out of science fiction.
They do have a certain mystique to them.
Totally. And we're going to unpack how this really abstract mathematical idea goes from the depths of pure theory to having these huge implications for how we understand the universe.
It's a wild ride.
It really is. And to get us started, you shared this awesome clip from an MIT OpenCourseWare lecture, and it's called Necessity of Complex Numbers.
I thought it was a great place to start.
It's a really intriguing title, too, right? I mean, it makes you wonder, like, why are these numbers so necessary?
It's not immediately obvious.
Not at all. So let's start at the very beginning. Picture this. You're a mathematician, you're wrestling with these complicated equations, and then bam, you hit a wall. You need to find the square root of a negative number.
Oh, boy.
And the math is basically saying, nope, sorry, it doesn't exist.
Exactly. Mathematicians actually thought that was the case for centuries. They struggled with this concept.
So what do they do?
Well, they eventually stumbled upon a solution, although at the time it probably seemed pretty bizarre, like a mathematical loophole almost.
Okay, I'm intrigued. Tell me more.
So they introduced this thing called the imaginary unit, I, and they defined it as the square root of -1.
Hold on, hold on. So basically they were like, we can't figure this out, so let's just invent something that lets us move on.
It might seem that way, but it wasn't totally arbitrary. The thing is, I wasn't just some random invention. It actually unlocked solutions to problems that were considered unsolvable before, like with polynomial equations, which, those pop up everywhere in math.
Right, right.
So by introducing I, mathematicians could suddenly find solutions where before there just weren't any.
It's like finding a secret door in a wall you thought was solid.
Exactly.
So this I, this imaginary unit, opened up all these new mathematical possibilities.
You really did.
Okay, but how do we actually use it? Like, how do we go from this imaginary I to actual numbers we can work with? And we're not just talking about, like, imaginary friends here.
Right, right. Well, that's where complex numbers come in.
Complex numbers. Okay, now you're just messing with me.
No, I promise it'll make sense. So complex numbers are usually written like this. A plus bi, where A and B can be any real number, the kind we use every day. And A, that's called the real part, and then B, that's attached to our new friend I. That's called the imaginary part.
Okay, so it's like mixing the familiar with the, well, the imaginary.
I like that.
But how do we actually picture this? It's not like we can just put I on our regular number line.
That's where the video's visual analogy comes in handy. Think of it like coordinates on a graph. The real part A goes on the horizontal x-axis, and the imaginary part B goes on the vertical y-axis. So instead of just a line, we've got a whole plane to work with.
Okay, so each complex number has its own spot on this plane. Like it has its own unique address in this imaginary world.
Precise.
I've got to say, it's pretty cool. It makes this abstract idea of imaginary numbers a little easier to wrap your head around. But are we just plotting points here? Or can we actually do anything meaningful with these complex numbers?
Great question. That's where the norm of a complex number comes in.
The norm. Okay, now we're getting really technical.
Don't worry, it's not as complicated as it sounds. Think of it like finding the size or magnitude of the complex number. Sort of like when we find the distance from a point to the origin on a graph.
Okay, I'm following so far.
The equation for the norm is z times z equals a plus b, where z is our complex number, and z, that's its complex conjugate.
Wait, back up a second. Complex conjugate. You have to break that one down for me.
Sure. The complex conjugate is basically like a reflection of the complex number across the x-axis. So if you have z equals a plus bi, then z is a minus bi. We just flip the sign of the imaginary part.
So it's like looking at the complex number's mirror image.
Perfect analogy.
Okay, got it. So back to this norm thing. You said we multiply the complex number by its conjugate. What makes that so special?
The really cool part is this. When you multiply a complex number by its conjugate, the result is always a real number. The imaginary part completely disappears.
Wait, so we go on this adventure into the world of complex numbers with their real parts and imaginary parts, and then boom, we can find our way back to the real numbers.
Exactly. It's like we're dipping our toes into the imaginary realm and discovering something very real in the process.
That's mind-blowing. I'm starting to see why these complex numbers are so much more than just some mathematical curiosity.
There's a lot more to uncover. And it gets even more mind-blowing when we start talking about Euler's formula, which is coming up in that video clip you shared. That's where things get really interesting.
All right, you got my attention. Lay it on me. What is this Euler's formula and what's so special about it?
Just imagine a mathematical equation so elegant, so profound, that it connects these totally different areas of math that seem completely unrelated.
Okay, I love a good math mystery. Go on.
That's Euler's formula. E to the power of I times E equals cosine of O plus I times sine of O.
Wow, okay, that looks a little intimidating.
I know it's a bunch of symbols, but just try to stick with me. What's incredible is that this formula brings together the exponential function, which we represent with the letter E, with trigonometry, those cosine and sine functions we all know and love. And it does all this through the power of I, our imaginary unit friend.
So what you're saying is this formula basically connects exponential growth to rotations in this complex plane we've been talking about.
Exactly. It's like a mathematical Rosetta Stone connecting these different areas of math that at first glance seem totally separate.
That's incredible. It's like discovering a secret passageway between different rooms in a mansion.
That's a great way to think about it.
But we're not just talking about some mathematical curiosity here, right? This equation has actual real-world implications.
It absolutely does. We see it popping up in unexpected places like physics and engineering.
Wow, that's amazing.
But perhaps the most mind-blowing example is its role in quantum mechanics. You know, the study of the very, very small atoms, subatomic particles, that kind of thing.
Okay, so we're going even deeper now into the quantum realm. I'm already feeling a little out of my depth, but in a good way. I'm ready. Let's do it. So we're diving headfirst into the quantum realm with these imaginary numbers. It's already getting kind of wild. So tell me, how do these imaginary numbers, these mathematical oddities, actually play a role in the world of atoms and particles?
Well, it's here in the quantum world where I really steps into the spotlight. In classical mechanics, you know, the physics of everyday objects, complex numbers were sometimes useful, but in quantum mechanics, they're not just useful, they're absolutely crucial.
So you're saying they're like baked into the very foundation of quantum mechanics.
Exactly. Like imagine the difference between using a calculator for something and then having the laws of physics written in a specific language. That language is what complex numbers are to quantum mechanics. See, in quantum mechanics, we describe the state of a particle using something called a wave function, often shown as the Greek letter F, spelled out psi. And guess what? This wave function, it's inherently complex valued.
Okay, so instead of a particle having like a definite location and momentum like we're used to in classical physics, we're dealing with a wave function that exists in this realm of complex numbers. No wonder it's so hard to wrap our heads around.
Right. It's like the particle is swimming in a sea of complex numbers. And the video you shared actually explains this beautifully. The professor talks about how if the wave function were only real valued, you know, if it only used regular everyday numbers, it would lead to all these contradictions in the equations that govern quantum mechanics. The equations would just fall apart.
So these imaginary numbers, they're not just some mathematical quirk, they're actually fundamental for describing reality at its most basic level. That's incredible. But here's what's been tripping me up. If these wave functions are complex valued, and we can only measure real quantities in the physical world like a particle's position or momentum, how do we connect the two? It seems like we're dealing with two separate languages.
That's the million-dollar question. And it leads us to one of the most mind-boggling aspects of quantum mechanics, the probabilistic interpretation.
Probabilistic. Does that mean things get a little fuzzy in the quantum world?
Fuzzy is a great way to put it. So physicist Max Born, he proposed that the square of the norm of the wave function, remember that gives us a real number, well, he said it's proportional to the probability of actually finding a particle in a specific state.
Okay, so let me get this straight. We take this complex valued wave function, we do some mathematical magic with its norm, and out pops a real number that tells us the probability of finding a particle somewhere.
You got it. It's like extracting a real tangible prediction from this abstract mathematical sea.
That's incredibly elegant, but also a little unnerving. So we can't say for sure where a particle is, but only the probability of finding it in a certain place.
Exactly. It's all about probabilities, not certainties. This is a cornerstone of quantum mechanics. At the quantum level, we're dealing with possibilities, not guarantees.
Which is a huge shift from classical physics, where we always thought if you knew everything about a system at a given moment, you could predict its future with complete certainty.
Right. And this shift from a deterministic view of the universe to a probabilistic one, it wasn't easy for everyone to accept. Even some of the pioneers of quantum mechanics struggled with it.
Yeah, the video mentioned how some pretty big names like Schrödinger and even Einstein weren't exactly thrilled with this whole probabilistic idea.
It's true. It's not every day you can say Einstein disagreed with this.
I know, right?
Yeah.
It's pretty amazing. So what were their objections? Why were these brilliant minds so resistant to this idea?
Well, Schrödinger, the very physicist who came up with the wave equation, he was uneasy with the idea that his equation, which he initially thought described a real physical wave, only gave probabilities. He actually came up with a thought experiment involving a cat to try to illustrate how absurd it seemed to apply these quantum probabilities to the macroscopic world.
Schrödinger's cat.
Yeah.
We have to do a deep dive on that one for a future episode. It's just too good to pass up. But what about Einstein? Where did he stand on all this?
Einstein, he played a huge role in the early development of quantum theory, but he famously opposed this probabilistic interpretation. He even said God does not play dice. Can you believe it?
Wow. He really stuck to his guns on that one.
Yeah, he did. Einstein firmly believed that there had to be a deeper level of reality hidden from our current understanding where things were deterministic, where particles did have definite properties, and the universe unfolded with clockwork precision.
So here we have these titans of physics, these intellectual giants battling it out over the very nature of reality itself. It's like witnessing a clash of scientific titans.
That's a great way to put it, and it highlights something really crucial. Sometimes the most profound discoveries in science, the ones that really change the game, they challenge our most deeply held beliefs about how reality works. The development and interpretation of quantum mechanics, it's a perfect example of that.
It's just amazing to think about these brilliant minds, like really wrestling with these huge questions about the nature of reality.
It really is. And the fact that this whole journey started with something as seemingly abstract as imaginary numbers, something that seems so disconnected from the real world, it makes it even more incredible. It's like they stumbled upon a hidden code within mathematics itself, and that code unlocked some of the deepest secrets of the universe.
It makes you wonder if those early mathematicians had any clue what they had started. Like, did they have even the slightest inkling that their equations would one day lead to such a huge change in how we understand reality?
I doubt it. It often takes time, sometimes even centuries, for the true impact of a discovery to really sink in. Imagine laying the foundation for a building without having any picture in your mind of what the final structure will look like.
And sometimes those seemingly insignificant pieces you lay down, they end up being the most important parts of the structure.
Exactly. It just goes to show you how interconnected knowledge really is. What starts as a purely abstract idea can blossom into something with huge, real-world implications, even if we don't fully get it at first.
It reminds me of that famous quote by physicist Eugene Wigner, "The unreasonable effectiveness of mathematics in the natural sciences." It's as if mathematics is the language of the universe and we're just starting to grasp its grammar.
Such a great analogy. It really makes you wonder what other mathematical concepts are out there just waiting to be discovered and used to unravel the mysteries of the universe. What kind of new perspectives might they offer? What seemingly impossible ideas could become the cornerstones of our understanding in the future?
It's exciting and a little intimidating at the same time. It's like we've barely dipped our toes into the vast ocean of knowledge.
That's the beauty of it. There's always more to learn, always more to explore. Each new discovery is like finding a new island, a new landmark on our map of knowledge.
And to think, our whole journey into this incredible world of complex numbers and quantum mechanics started with a simple question. What's the square root of -1? Who would have thought something so abstract could lead to such profound insights?
It's a good reminder to never underestimate the power of curiosity. The most groundbreaking discoveries often come from the most unexpected places.
Absolutely. And for anyone listening who might be feeling a little overwhelmed by all this talk of complex numbers and quantum mechanics, just remember, every journey begins with a single step. Or in this case, maybe a single I. Who knows, maybe you'll be the one to discover the next imaginary concept that changes the world.
Now that would be something.